All right, what do you say we begin? Okay, hi everybody. Welcome to today's session. My name is Linda Calais and I will be your MC moderator for today. Today's session is going to be led by Deep Moitra. He's a research software engineer of Google and is working at the Google Brain team in Montreal, working on program synthesis. He's been at Google since 2015 and has previously worked on Dopamine, a library for deep reinforcement learning, and Google Vizier, a service for Bayesian optimization and auto ML. And before Google, Deep obtained his PhD in applied machine learning from Carnegie Mellon University on generative models of protein sequences. At present, he lives in the suburbs with his wife and 2 cats and enjoys the outdoors of the Laurentians. So please welcome Deep in today's session. I will go off camera, and everybody, please, just as a reminder, if you have any questions about the session, please post them in the chat and I will take them up after the session.
Cool. Welcome everyone, and thank you for tuning in globally wherever you're from. The topic of today's talk is deep learning for program repair. Deep learning has been in the vogue for the last several years, and this talk is going to look at applying deep learning techniques for the task of repairing software programs. So, is this an important thing to do? A study from last year said that IT companies are spending in the order of trillions of dollars in dealing with their IT services costs. Interestingly, even in this COVID-19 pandemic, while we're all hunkered down in our respective houses, the tech industry is booming and bustling away. What's also interesting is that IT companies spend a lot of money and a lot of time dealing with bugs and outages and quality of software issues with respect to IT services. So for those of us for whom programming is bread and butter, you know that it's not sunshine and rainbows every day. There are times when crazy things happen in production. So the software development process can be painful and frustrating. So here's the pitch. The pitch is that wouldn't it be great if deep learning could help with that? It would certainly make for the stuff of dreams, right? And so in particular, what are we exactly talking about? So I'm talking about an area of research called ML for SE, machine learning for software engineering. This area of emerging research attempts to aid software development through machine learning. It's good to also clarify at this time what it's not. It's not SE for ML. So this is probably what we're more familiar with. These are the tools, the libraries, the frameworks, such as Spark and Apache that go into helping with machine learning. We're not talking about that. We're talking about machine learning just for helping software engineering. Okay. And what's all the interest and bustle about this area? It's because there's an emergence of data that's coming together, and ML for SE is at a good time to be powered by it. So just consider GitHub and all the code repos out there, including all the big tech companies that dedicate resources to writing code there. And it's not just source code; it's also test results, bug reports, code review processes. These are all useful data that could help in the software engineering process. So just to recap a little bit, I described this machine learning for SE field to you, and now we're going to focus our view a little bit to concretely talk about the approach we're looking at. And so we're looking at an approach about how to learn to edit software. And to motivate this a little bit, I'm just going to throw this screenshot of a commit on a GitHub project. This is a random commit to the JAX project. The typical code commit UI is in effect here. So the stuff on the left is code that was before, and the stuff on the right that is code that was after, and the red things are the stuff that changed in order to become the stuff on the right. Okay, so the crux here is that if we could learn to mimic these patterns, what the developer is doing, by looking at these small changes to large projects, we could probably begin to do something useful. And so when we're talking about patterns, what are these patterns? Like what pattern are we mining? And so I'll posit to you that graphs are actually useful in mining these patterns. So consider the simple example of 2 lines of code that changed. So the stuff on the left changed the stuff on the right. And notice that this change was a change in this binary operator plus that became a minus. What's interesting can be naturally represented as graphs. When you build your program, you run it through a compiler, and the compiler internally constructs an abstract syntax tree of the code. And it's not just a binary tree structure. It could be an arbitrary graph. For example, if your static analyzer detects that the variable being referenced in line 2 is actually defined in line 1, then you could just draw an arrow connecting an edge between these 2 nodes. So you can create arbitrary graphs. When you're talking about edits, you also should describe what the edit looks like, right? Because you want to edit the thing on the left. And so what's important is that we want to know where to edit. We want to know what kind of edit and what the edit is. Specifically, we want to say that in this example, we want to have a pointer to this plus node here and specify that the operation is an update. It could be a bunch of operations such as insert, move, delete. But we want to say this is an update. And we want to specify that the update is a change to a minus. Okay. Finally, we want to plug this in our machine learning framework. We're going to pass this through a graph-to-diff neural network. That's the model we'll be referencing in the following slides as well. This graph-to-diff neural network architecture will allow us to take a state of code represented as a graph and output a sequence of edits in a domain-specific language that tell us how to modify the graph to get what we want. Okay, so just to summarize what I've said so far, we're interested in learning how to edit software, and we want to mine patterns about editing software. And we're going to represent these patterns as graphs that are edited with a specific domain-specific language using a graph-to-diff neural network. Okay? And so now to turn this approach of learning to edit software into a more useful application, we're going to look at how this approach of editing software might be used for repairing programs. So I want you to imagine, I want to imagine that you're a Java developer at your favorite tech company, and it's lunchtime, it's 12:30 in the afternoon, and your buddies are calling out to you to go down for lunch. And you're almost ready to get up from your chair to go down when you see this nasty compiler on your screen. Can't find symbol foo mask. It's certainly a damper. But you're a trooper, you don't like leaving things unfinished. So you decide to work for the next 5 minutes and fix the build error. Now, if your tech company has a sophisticated developer workflow, they probably stored logs of these interactions. So in particular, they might have stored the state of the broken program. They've also stored the compiler error that was provided as a hint, and also the state of the code when it was fixed. Enter machine learning. We can turn this into a learning task. We can go from the state of the broken code to a diff that fixed the broken code. To make this very specific, the question that we are asking, the challenge that we're giving ourselves is that can we predict the exact fix that a professional developer applied? That's the challenge. And it's not an easy task. So I'm going to dive into some code examples to show you that it's not trivial to solve these kind of problems, right? So what I have here is a chunk of code, some code that has an error. And the line in red was what was wrong with the piece of code. And the line in green was what the change that was made to fix it, right? On the left is the diagnostics that the compiler gave, saying, here's what I think is wrong with your program. So you can see that the compiler diagnostic complained that at line 10, it can't find the symbol long name. And similarly, at line 15, it mentioned the same thing. Now, if you squint really hard, you'll notice that this long name is camel-cased, whereas the original definition did not have camel-case. It was a typo. And the fix was kind of simple, to change it to camel-case. So what's interesting to notice here is that the compiler does not correctly localize the fault. It thinks there are two errors in different locations, but the fix was somewhere else and it was a single fix. Okay, so these fixes can often not be trivial to solve. It can be a little bit tricky. Going back to our learning to edit software framework, we're going to take this and plug this into the graph architecture. So we're going to represent our broken state of code as a tree, an abstract syntax tree. And hey, the compiler gives us extra information. Why not use it? So we can turn it into a subgraph represented by this thing here. You can just define arbitrary subgraph that's useful, plug it in to the existing graph, push it through a graph-to-diff neural network, and generate a diff that resolves the errors in the graph. Okay? So you might ask, what is all this fancy graph stuff that's going on? Do we really need graphs? Can we not do something simple? Sure. So an alternative competing approach could be to treat it as a sequence-to-sequence problem. We want to take a sequence of something, say code, to a sequence of something else that fixes the code. This approach was tried by Mesba et al. They turned the program graph into a input sequence, and they try to generate an output that tries to fix the input sequence. The issue here is that the output becomes imprecise. It's no longer possible to exactly point to a node in the input graph and say, I want to fix this. Instead, what you get is like changing tokens that are not precise. So you can say, for example, I think int should be changed to string, but then which int? Like, because if you have a program with a bunch of ints in it, I don't know which one to fix. So there's the task here is to actually, something is lost when you don't point to the exact right thing. But this graph-to-diff approach makes it a harder task to exactly predict what we're trying to change. So does it work? So in terms of accuracy numbers, this is test accuracy. Did we exactly get the fix that the developer made? The sequence approach gets 10% test accuracy, while the graph-to-diff approach gets around 26%. Okay, some of you might be wondering, and this is a question we often get, is doesn't 26% look kind of low? Like, don't we get like 99% plus in machine learning all the time? That's a good question. And the observation here is that the task is different. It's much more challenging, and the metric is a lot harder. So the domain, as you can imagine, fixing computer programs is hard. On top of that, we're not satisfied with a fix that kind of looks like a right fix. We have to exactly get the right thing, otherwise it doesn't build. So the analogy would be imagining you're translating between English and French. It's okay to have a French sentence that is kind of like an English sentence, the translation of the thing that it should be. But in a compiler build language, it has to be the exact same thing. There's no room for errors. Okay. And so we talked about, one story was looking at the numbers, but another approach could be to look at the qualitative results exactly. Okay. So here are 4 examples of fixes that the model got correct. Let's take one example. Okay. So just as before, the thing in red was the erroneous line, and it was fixed by the thing in green. So Java developers will notice that this is a kind of pattern called the builder pattern. So on the right-hand side, we're trying to construct an object and assign it to the thing on the left-hand side, but the type is not agreeing. So if you look at the compiler diagnostic, it says builder cannot be converted to widget group. It's not, type is not matching, right? And so if you recognize this builder pattern, it's like you sequentially construct an object with a bunch of parameters, and then you call build at the end to create an object of that type. And so what's missing is a .build statement at the end. And this is a common mistake that developers make. And so it's useful that the graph-diff model can catch these kind of errors. That's probably a simpler fix. Now let's look at example number 3. That's a harder fix. Like, notice what's going on. This long name response was not the right approach. It should have instead been a listenable feature that was type applied of long name response. And what's interesting here is that this edit is actually a complicated edit because it involves inserting, it involves type applies, it involves a bunch of different things. I got a question here from Kamal. Is the performance based on all of the compiling errors that you could find in Google's database? Or did you select some type of errors to work on? Yes, so we definitely restricted our errors to Java build errors of certain types. We also did some filtering to make sure that we weren't handling errors that were like across multiple files. So the scope of the problem was definitely restricted, but we still got like a database of 500,000 errors and fixes. Okay, proceeding on. It's encouraging that the performance keeps going up with more training data size. So on the y-axis, we have the validation accuracy. On the x-axis, the size of the training data set. And you'll notice that this performance isn't plateauing anytime soon. So this is encouraging because as we harvest more data, as we have more databases to mine, we can keep getting more oomph in our performance. Finally, while it's good to celebrate the successes, it's also useful to look at the failures. What did we get wrong? And can we learn something from it? And so I'm going to show you 3 different examples, and they vary in their usefulness, even though they're wrong. And wrong in this sense is, did the fix match exactly what the developer did, right? So that's what we're looking at. So all these fixes built correctly, but they're not what the developer did. So let's look at the first one. The first line is the ground truth. This is what the developer did to fix an error. They probably an assert false statement was missing in a unit test, and they decided to insert this particular line, import static junit.framework assert false. So our model predicted something different, but it's actually better. Like the arg.junit package is more popular and more useful than the first one. So it didn't get the exact same thing, but it probably got a better thing. The second one is not better. It's like it's worse than before, but it's still useful. So the original error was that something was wrong with this method name, the original method name, and the fix was to use a different method name. The graph-rediff model predicted a different method name. It didn't get the exact same thing, but it's still. Karthik is asking a question. I don't know the architecture of graph-to-diff. I can show that to you in a moment. There are some appendix slides on that. Okay, so back to this particular example. So it's useful that the model got pointed out that something's wrong with the method name even if it didn't get it. So it's worse, but still useful. And finally, I want to show you an example where it gave a fix that's just plain wrong. It's a bad suggestion. So what's wrong is something to do with this parse long things. But this piece of logic here is checking equality with 0. Our model instead suggested inequality with 0. This is logically and semantically wrong. So it makes mistakes, and sometimes these mistakes are egregious. So just to recap this section a little bit, I wanted to mention to you that this graph-rediff approach is building on this learning to edit software approach as well, and it's getting interesting and encouraging results. And so it's definitely useful. It's not perfect. It makes mistakes, but still quite useful. Okay, to answer Karthik's question about what does the model look like, I'm just going to go through the appendix slide. So we have, so this is a graph-rediff neural network architecture. It has 2 components largely. It's got an encoder and a decoder. The encoder is a graph neural network which will take your program graph and diagnostic information in a graph, run a few iterations of message passing. It'll get like a hidden set of nodes. And then there's a decoder section, which is a transformer style approach, which, as Karthik mentioned, has attention mechanisms in it. But what's interesting is that the output is not like a sequence of tokens. Like the outputs is like 3 specific kind of modules. It's got like the regular token, but it's also got copy and pointer. So the copy is useful because a common problem in software engineering is that your identifiers are typically out of vocabulary. There's just so many different types of variables and identifiers that it's not possible to have all of them in your training data. So this copy mechanism says that copy something from your input example at test time so that you still get the right thing. And the pointer mechanism actually is pointing to something in the input example to know what to fix. So it's a transformer with additional output heads, and we have to do some kind of mechanisms to make sure that it's doing the right thing. If you're interested, like there's a link here in the slides. We have like an archive paper, Learning to Fix Build Errors with Graphic Neural Networks, that has more details. Okay, so to like sync back a little bit. Oh yeah, so I'm coming to the end of my talk, essentially. I just want to like finish with some concluding thoughts. So we want to say that to be useful to the developer process, we should learn from the developer process. That is like, if developers like show us how to like edit sequences, then we should learn from that. And finally, we're working on training big machine learning models in this data stream that we have at Google, and we have good results. And we're super excited about the future. We think this area of research is definitely is growing and has a lot of potential impacts. I wouldn't be surprised if this is the next big thing in machine learning in the future. Finally, get in touch. Here's some contact information. And I'm happy to take questions at this time.
Awesome. Thank you so much for that session, Deep. That provided some practical examples of how this could be used, and I think that was really interesting. I'm just looking at the chat for questions. You answered one of these questions. There was another one that came in about if you could explain more about the architecture of Graph2Diff. Are you using some kind of attention mechanisms to solve this ML4 software engineering problem?
Cool. So I think I answered the first two. There's another question that's coming up from Abhishek. Can a similar kind of approach work for writing tests for code? Yeah, that's interesting. So I just want to like preface this by saying that this general area of research under machine learning for software engineering falls under program synthesis. Program synthesis is, as you can imagine, is synthesizing programs that do a certain task. I touched on how to like repair programs, but you're right that there's like other related approaches that will help in writing test cases. Like for example, you give the specification saying that I have this input, I want this output. Can you generate like test cases that do this? So yes, there's certainly some approaches around this. This particular approach doesn't do that. I think it's out of scope, but definitely there might be related approaches that touch on that area.
You see there's one more question that came in.
Yeah, that's super interesting. How can we improve the performance of the accuracy spiking neural networks, BERT? I haven't thought of spiking neural networks, but BERT is something that we're actually looking at right now. Because while we have training data, we also have like a bunch of unsupervised data, right? Like we have just raw examples of code lying around. And so we can definitely train BERT-style models and pre-train our models to get that extra oomph. So maybe watch out for like papers in the end of the year. We might have some interesting results on that.
Awesome, thank you. What would you say is next for your research currently?
So yeah, like the previous question, we're just looking at if we can leverage pre-training to help our models go forward. That said, we're also like in talks with production teams and trying to push it and make it useful for developers, not just research projects. Actually want it to be useful inside the company.
In the real world, okay, interesting. Cool. Don't see any other questions in the chat, but I have a question about what is a day in the life of a Google Brain employee.
Oh, right now it's getting up at odd times and playing with my cats. Uh, but in general, yeah, I guess it's like a academic research lab. So you have a mix of research scientists and engineers who are more closely aligned with product teams. A lot of folks have affiliations with universities. So there's a very strong presence on university campuses and talks and all that. So yeah, it's a very academic culture. There's emphasis on writing papers, but there's also emphasis on building software.
Mm-hmm.
Me personally, I take the train every morning. I used to take the train every morning because I live in the suburbs. So I do enjoy like the quiet time I get in the morning in the train to watch cat videos, or I'm saying cat too many times. I shouldn't say that, but just like whatever, like do my fun thing or read papers or whatever.
Yeah. Interesting. Awesome. Thank you so much for presenting today. It was a really cool chat. If anyone else has any more questions, feel free to write in the chat here. There's also networking going on afterwards. And Deep has shared his info if you want to get in touch with him. But yeah, thank you all very much for today's session.
Thank you all for attending. I really appreciate you, audience, and there are several good questions. Thank you.
Yeah. Thank you, Deep, and thank you for everybody attending. Awesome.
Bye-bye.
Okay. Bye, everybody.